All right, if you're a developer, chances are you use GitHub every single day. But have you ever really stopped to think about what's going on under the hood? Well, today we are pulling back the curtain and diving deep into how GitHub actually works.
You know the feeling. You type git push, hit enter, and boom! A few seconds later, your code is just safe. It feels like magic, right? But what is that magic? What's really happening in that tiny window of time?
Well, it's not magic. It's an incredible journey. Your code is actually traveling through this custom-built, planet-scale machine that's been engineered from the ground up to be insanely fast, super resilient, and totally secure. And the whole thing is built around one central philosophy.
And this right here, this is the heart of it all. See, while the rest of the tech world was chasing microservices, breaking apps into hundreds of tiny little pieces, GitHub did something different. They doubled down on what they call the majestic monolith. And the idea is actually pretty simple. Keep all the main business logic in one big, powerful application. This helps their developers move super fast. But for the really tough problems, the things that need to operate at a massive scale, like storing your code or searching it, that's when they build these incredibly specialized custom systems.
Okay, so let's follow the path of that Git push. The very first stop on its journey? It's got to get through GitHub's front door, the layer that greets every single request from every corner of the planet. And you might think it's just some standard load balancer, but no way. This front door is a completely custom-built open-source system they call GLB, and it was engineered to solve a very specific problem. How do you juggle millions of different types of connections? You've got quick web page loads, constant API calls, and those really long stateful connections that happen every time you git push or git pull.
So how does GLB do it? Well, its design is just brilliant. It's a two-tier system. First, you have these things called directors, and you can think of them as the fastest traffic sorters on the planet. They use a special trick to bypass the slow parts of the Linux kernel and talk directly to the network hardware. I mean, we're talking millions of packets per second. Then, to make sure your connection always goes to the right place, they use this clever hashing trick. It basically means every single director just knows where to send your data without ever having to talk to the other directors. They don't share any state. It's so cool. And because of this, they can do rolling upgrades, major surgery on the system during peak hours, and you, the user, never even notice. Not a single connection dropped. Amazing.
All right, so GLB has done its job. Our request is safely inside the network. And now we've reached the brain of the operation, the majestic monolith itself.
That's right. At its heart, GitHub is one massive Ruby on Rails application. And I want to be clear, this isn't some old legacy code they're stuck with. No, this is a very deliberate, strategic choice. Having one big, coherent codebase means their developers can move incredibly fast. They're not stuck trying to coordinate changes across dozens and dozens of tiny services. In this whole philosophy, it extends to the front end too. I mean, think about it. We live in an age of these huge, heavy JavaScript frameworks, right? But GitHub's website, it just feels snappy. So how do they pull that off? Well, by basically doing the exact opposite of what everyone else is doing. They use this amazing technique called hotwire, which literally means HTML over the wire. Now, normally, a site sends your browser a bare-bones page and a giant pile of JavaScript, and your browser has to do all the work of building the user interface. But with hotwire, the server does the work. It sends fully formed HTML. So when you click something, it just fetches the new piece of HTML it needs and swaps it in. You get that super responsive, app-like feel, but with the speed and simplicity of old-school server rendering. It's kind of the best of both worlds.
And the benefits of this server-first approach? They're huge. Pages load way faster. The site is more accessible by default, and honestly, the code is just simpler to write and maintain. Now, that's not to say they never use a framework like React. They absolutely do, but only where it makes sense. For really complex things, like their project boards, they'll use React, but they treat it like an island of rich interactivity, sitting on an ocean of server-rendered HTML. It's just pure pragmatism.
Okay, so the application has processed our request. Now we get to the most important part of all. I mean, the absolute crown jewels. How do they store your code and make sure it is never lost? This is where GitHub's custom engineering really truly shines.
You know, back in the day, GitHub used a pretty standard approach, basically just mirroring disks. But there was a huge problem with that. If the data on the main server got corrupted for some reason, that corruption would be instantly and perfectly copied over to the backup. It was a disaster waiting to happen. So they realized they had to build something totally new, from scratch, and they called it spokes. So here's how spokes make sure your code is safe. It's called a quorum write. When you push your code, a proxy sends it to 3 separate servers, all at the same time. Each of those servers checks the data on its own to make sure it's not corrupted. And then the system waits. It waits until at least 2 of those 3 servers report back and say, yep, I've got the data, and it's good. That's the quorum. Only then does it send that success message back to your terminal. Think about that. Before you even see success, your code is already confirmed to be safe and sound on multiple machines. It's an incredible guarantee.
But it's not just about the code, right? What about all the metadata around it? We're talking about all your issues, your pull requests, your comments. That's petabytes of data. For that, GitHub uses a system called Vitess. It's an open-source tool that basically acts like a brilliant traffic cop, sitting in front of hundreds of MySQL databases, and it makes them all look like one single gigantic database to the main application.
And the secret sauce to making this all so fast is how it splits up, or shards, the data. The key it uses, the repository ID. This is so smart. It means that everything related to one repository, all its issues, its PRs, its comments, it all lives together on the same physical machine. So when you load a repository's page, the database doesn't have to go on a wild goose chase across hundreds of servers. It knows exactly where to look. It just goes to one place. That's why it feels so instantaneous.
Okay, so our Git push is complete. The code is stored safely, the metadata is all updated. But believe it or not, the journey isn't over yet. That one push now triggers this massive ripple effect, kicking off work in a bunch of other highly specialized systems.
First up, GitHub Actions. You know that little green checkmark or that red X you see next to your commits? That's GitHub Actions. It's a gigantic distributed computer that springs to life when you push. It can run your tests, build your application, even deploy it to production, all automatically.
And the magic behind Actions is how it manages to run all of this untrusted code from millions of users, both securely and at incredible speed. Here's how. Every single job runs in its own tiny, disposable virtual machine using a technology called Firecracker. Now, a normal virtual machine might take a few minutes to boot up. A Firecracker micro VM boots in under 125 milliseconds. That is literally faster than you can blink. So you get this ironclad security with almost zero performance penalty.
Okay, and last but not least, once your code is on GitHub, it needs to be searchable. But searching code is a really hard problem. It's not like searching a book. Think about it. Traditional search engines are designed to ignore things like punctuation and capitalization. But in programming, those things are everything. Searching for myclass.new with a regular search engine would probably just give you results for myclass and new, which is completely useless.
So, what did GitHub do? Yep, they built their own search engine from scratch. It's written in Rust, and it's called Blackbird. And its core idea is pure genius. Instead of seeing words, Blackbird sees overlapping 3-character chunks called trigrams. Just look at the example. myclass.new gets broken down into these little pieces that preserve everything, the capitalization, the dot, all of it. This lets you do incredibly precise, literal searches across trillions of lines of code and get results back almost instantly.
So let's take a step back. We've gone from a simple Git push all the way through a global network, into a majestic monolith, through a self-healing storage system, and into a custom-built search engine. So what's the big takeaway from all this? At the end of the day, it all comes down to a philosophy of pure engineering pragmatism. There are really 3 key lessons here. First, the monolith isn't a bug, it's a feature. Use it to maximize your team's speed. Second, specialize only where it hurts. Don't build custom tech for fun. Build it when you hit a wall that existing tools just can't break through. And finally, number 3, assume everything will fail. Design your systems from day one with the expectation that things will break and build them to heal themselves.
It's this beautiful balance of boring and bespoke technology, right? It's a powerful reminder that it's not about using the flashiest new thing, it's about using the right tool for the job. And that kind of leaves us with a great question to think about for our own projects. Where can we gain an advantage by keeping things simple? And where do we really need